What's up, everybody? Welcome to Lecture 30. Lecture 30 is all about Section 3.8. Now, 3.8 is about this idea called Newton's method. And to talk about Newton's method, I thought it'd be best to give you a demonstration of the idea in practice before we actually get into the math of Newton's method. So let's imagine we've got this parabola here. Y is equal to x squared minus pi squared. Well, since we're good math students, we know that this can be factored as x minus pi and x plus pi. So this thing is equal to 0 at negative pi, at x equal to negative pi, and at x equal to pi. But let's assume we didn't know we could factor it. Let's assume we had no idea that we could do that. Maybe our number is something a little more esoteric. Maybe it's a prime number. So it's x minus 17. Then we wouldn't know where that root is. I mean, we could work it out and probably figure it out. But for right now, let's just operate under the assumption that we don't know our roots of x squared minus pi squared are at negative pi and at pi. But we wanted to find them. So we look at it, and we look at it, and we look at it, and we come up with this idea. Instead of thinking about it backwards, say, you know, I could kind of zigzag in a little bit. I could do that by saying, let's pick some point over here, and let's form the line tangent to that point, go all the way down to the x-axis. So where y is equal to 0. Now, we're going to call this x1, y1. And we're going to call this point x2, comma 0. Excuse me. So now, we take this x2 point and we go back up to our function. So this will be x2, comma y2. And we form another tangent line. And we follow it down to the x-axis. And we get a new point, x3, comma 0. And we keep doing this, and we keep doing this, and we keep doing this. Notice, though, if we do, we're going to get closer and closer and closer to that place where our function is equal to 0. Well, one of those two roots, anyhow. And we get closer to that case where x is equal to pi. This is what Newton's method is doing. It's saying, all right, give me some function. I think this function has zeros or roots. I'm going to take and use tangent lines, trace them back down to the x-axis, so where y is equal to 0, use that as a new x value, go back up to my function at that new x value, and I'm going to repeat the process. And I'm going to zigzag into the roots. This is the idea of Newton's method. This is what Newton's method is doing. It's basically just saying, take a guess, any guess. You're going to call that x1. Cool, we got x1, find y1. Cool, you got y1, find the line tangent to your function at the point x1, y1. Follow that down to the x-axis. That gives you your new x2. Now go up to x2, y2. Form the line tangent to your function at that point. Follow that down to the x-axis. That gives you x3. Go up to x3, y3. Form the line tangent to your function at the point x3, y3. Follow that down, and so forth, and so on. This is all Newton's method is. Now, the new question is, what does that look like? Like, what is the math there? How does this work algorithmically? Well, this works algorithmically by making a couple of different observations. And to show you those observations, I'm going to go ahead and erase the board and kind of break some of this out a little bit. So stick around. Okay, so to explain the math and what this is going to look like, we're going to assume we've applied this n many times. So we're looking at the nth x value. After doing this n many times, we're now at xn 0. We go up to our function to the point xn yn, and we form the tangent line. So the line tangent to our function at that point. And that tangent line, it's going to look like y minus yn equal to f prime at xn times the difference x minus xn. So y minus yn times our derivative of our function at xn times the difference between x and xn. Okay, well, we need to find this point down here, this xn plus 1, don't we? We know a few things happened there, though. We know, one, that y is equal to 0 there. And we know that it has to sit along this line, right? So why don't we rearrange some things here? Actually, before we start rearranging some things, let's just work out what this looks like down here. If we follow this all the way down to where y is equal to 0. We know this is going to look like 0 minus yn is equal to f prime at xn times, well, our x value is xn plus 1 minus xn. So we look at it for a little while, and we say, you know what? We can move some other things around. We can rewrite this yn as f at xn, that's negative, is equal to f prime xn times the difference between xn plus 1 minus xn. Okay, well, we could now divide out this f prime of xn. So when we do that, we get negative f of xn divided by f prime of xn is equal to xn plus 1 minus xn. But look at what happens now. We can solve for what this x value is. This x value is equal to xn plus 1 is equal to xn minus f of xn divided by f prime of xn. Okay, well, how does that help? Well, think about what this method is doing. You're zigzagging up and down between your function and the x-axis until finally your function reaches the x-axis, until you're at your root, right? In other words, you're searching for every xn plus 1 until it just stops, right? So this will zigzag up and down, 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 up and down. Until y is equal to 0. And when y is equal to 0, it just stops. Another way of saying that is this sequence converges onto a root or a 0. In other words, start with a guess. You're going to call that x in it. Let's call it x1 for now. You start with your guess. You plug it in. It gives you x2. You plug that back in. It gives you x3. You plug that back in. It gives you x4. And you keep doing this forever, until you converge. That's all this is. That's all this does. This is how your computer actually works. Most of the time, this is how it used to be done on computers. I don't actually know if they still commonly use this method, or if we have another better method. I would guess that this is the first case that we applied. But this is a big chunk of what computers are doing. This is used in all sorts of different algorithms. And it's because it's time efficient for a computer to do it. It's not time efficient for you or I to do it. Like, by no means am I going to make that claim. This takes a while, right? Yeah, it takes a long while. I'm not going to lie, guys. But the computer does it pretty damn fast. Because a computer does it so fast, it's one of the first things we applied it to. We're like, cool, solve this problem, solve this problem. And that's how it got used. This is called a numerical method, for whatever that's worth. Or this is a branch, or this is from a branch, or an example of a branch of mathematics, known as numerical methods. Numerical methods are algorithmic approaches to solving math problems. It's a pretty cool branch of mathematics. If you're a computer scientist, get used to it. If you're an engineer, get used to it. I actually know quite a few engineers who complain about having to use this from time to time. This is another thing called Taylor's method. If you're a physicist, get used to it. These are techniques that are pretty common in those fields, these numerical methods. And that's because a computer can't actually solve most problems exactly. And the reason why is because of what's called computer error, or machine error. Machine error is accurate up to 16 digits. So you can only get 16 digits of accuracy in a number from a computer without some fancy coding. You can assign more memory blocks, but that's neither here nor there. So because a computer can only be accurate up to 16 digits without extra work, none of its answers are exact. You can't just give it a bunch of math, say integration, and expect it to come out with an answer. Take, for example, the number pi. Pi has an infinite number of decimals. A computer can only hold 16 digits, so anytime you do anything with pi, it's an estimate up to 16 digits. For that reason, mathematicians, computer scientists, engineers, and physicists, and chemists and biologists to some extent, have decided, well, we need a new branch of mathematics. This came around way back when. Like, it's Newton's method because it's of Newton, and we've known about it forever and a day, but it wasn't really practical until computers came around. At that point, we were like, yo, some of these ideas are useful now. We started investigating them, and they led to this whole branch called numerical methods. And this is an example of that. Having said that, it's not always perfect, unfortunately. By the way, because I just realized, this is prime, so if you weren't able to tell, that is f primed in the denominator. But I digress. So this isn't always perfect. Sometimes it can get things wrong. Sometimes you can start with a value that just doesn't converge. So in other words, it doesn't draw in on a number. There is a particular type of fractal that is an expression of that idea. It's called Newton's fractal. It's a fractal formed from Newton's method. There's actually a great 3 blue, 1 brown, or whatever that YouTube channel is called. Great video on it. But yeah, this is Newton's method. This is the idea of Newton's method. Newton's method does not always work. Sometimes it does fail. Now, how are you going to be expected to use this in class, in your homework? Really, you're going to be given a function and told to approximate it within so many iterations. They might give you a starting point, or they might tell you where the end point is and expect you to start with some sort of a starting point. They might give you examples where Newton method fails, and you need to be able to identify that. And the way to identify that is just really checking, seeing if the math works out. So having said that, that was really all I had on this lecture, guys. Guys and gals. So, y'all are free to go. If you have any questions, by all means, drop me an email. I do apologize for not being able to make it at office hours today, but making them up tomorrow. So be there. I'm not going to finish the rest of that. Be there, be square, like you've heard enough geometry from me. Also, do remember your homework is due Friday. You have an exam Friday as well. Do be there. Yeah, have a good one, everybody.